talks for Renewables, Empowering Earth and Sustainability, or TREES talk series. We have done 16 talks under TREES talk series, and this is 17th talk today. This talk is given by Dr. Amrith Bhide. He is an associate professor and head Department of Physics at NIT Puducherry. He completed his MSc and PhD from IIT Madras. Earlier, he completed his BSc from Mangalore University, Karnataka. He has 2 postdoc stints in Germany, one at Institute of Physical Chemistry, Justus Liebig University, Gießen, and the other one at the Institute of Physical Chemistry, University of Münster. He has received several awards, notably Outstanding Faculty Award for the contribution and achievement in the field of solid state ionics. Dr. Bhide has published more than 15 research articles in reputed journals, presented papers at several conferences and workshops. He is going to talk today regarding Introduction to Solid State Ionics. The abstract of this talk reads as follows. The science and technology of ionic materials in general, and fast ionic materials in particular, is termed as solid state ionics, or SSI. This interdisciplinary field of material science, physics, and solid state electrochemistry deals with the preparation, characterization, theory of solid electrolytes and their applications in solid state electrochemical devices. So this talk will be focused on fundamental aspects of different solid electrolytes and recent progress which are found to be extremely useful in solid state electrochemical devices such as batteries, fuel cells, sensors, and electrochromic displays. So I invite Professor Bhide to please share the screen and start the presentation. Professor Bhide.
Thank you, Pravinji, for introducing me and giving me this opportunity to be part of your tech series webinars, and extremely happy for that. And I think this may be the year-end seminar, right? Hopefully. And
yes.
I'm sharing the window shortly. Yes. Is it visible?
Yes, it is visible.
Slides are moving?
Yes.
Okay. So today's talk series, I'm very much delighted to share some of the basic ideas of solid state electrolytes, and the whole field is considered as named as solid state ionics. And I have used a couple of images from different articles and my own work. This is for just education and fair use only, not any other commercial use. With that, I will start the talk. As we know that solid state ionics is concerned with science and technology of motion of mobile ions in solid state. So this discipline of research is encompass remarkably wide range of themes in both basic science and applications. So it has both basic aspects of science, fundamental science, as well as applications. If you look at this diagram, solid state ionics is a multidisciplinary or interdisciplinary area where it contributed get from physicists, material scientists, computational scientists, solid state electrochemists, and engineering people. And if you trace back the word solid state ionics, it was first time coined from the Japanese scientist Professor Takehiko Takahashi in late 1980s. And if you go back, the origin of these ionic materials, our own well-known scientist Michael Faraday, he has established that lead fluoride and silver sulfide are the first ionic which exhibit ionic conduction, and he has established them in at 1838 itself. But it took nearly 100 years, over a century, to get these materials for the application. And at present, if you are using our mobile phones or our any gadget, electronic gadget, which is running by batteries, rechargeable batteries, or primary batteries, this because of the whole evolution that has happened after establishment of ionic motion, and which is reported at 1838 itself. So let us see some basic definition of the solid ionics. That is, these are called as fast ionic conductors or solid electrolytes. These materials exhibit ionic conductivity at ambient temperature or far below the melting temperature. So this is something unusual. Normally, materials don't show ionic conductivity at ambient temperature, or unless you go to the melting point, the materials don't show ionic conductivity. But these materials show ionic conductivity either at ambient temperature or far below the melting temperature. That's why the term superionic has been formed. These materials also called as fast ion conductors because they have huge mobility, and they're also called as solid electrolytes because they are used as electrolytes in energy applications. How do you recognize a material is supposed to be ionic? They exhibit ionic conductivity of the order of 10 to the power minus 4 to 10 to the power minus 1 Siemens per centimeter, which is almost like liquid. These materials exhibit liquid-like conductivity in the solid state itself, and you consider their electronic conductivity, they're almost like insulator. And if you want to characterize, or if you want to say a material is supposed to be a ionically conducting, then there are two things: transference number. Ionic transference number is the ratio of ionic conductivity to total conductivity, which tend to unity. In other way, you can also establish the fact that electronic transference number is tending to very small. Like here it is 10 to the power minus 4. Why people have to go for solid electrolytes? For the following reason: when you use solid electrolytes, they will give you a long storage life for your device. They can be used for a wide range of temperature, and they give you compact structure. We are all nowadays 21st century, everybody is going for miniaturization. So these solid electrolytes will give you compact structure, and there is no question of leakage or volatilization of the electrolyte. So these are the basic advantage why people are looking for solid electrolytes. If you see this classification, here the solid state physics can be viewed as conductors, and you can study about superconductors, semiconductors, and a part in between is ionic conductors. And ionic conductors has two classifications. One is liquid electrolyte, and another one is solid electrolyte. When we speak about solid electrolyte, we say that the field is solid state ionics. Why the term superionic used? Or here I am giving a basic difference between normal and fast ionic conductors. A fast ion conductor, as I told before, it shows liquid-like conductivity, or it shows conductivity at far below the melting temperature, like silver iodide. I'll come to this point little later. And else, normal ion conductor, they are basically insulators, and if at all you are finding ionic conductivity when it almost reaches to melting point. In the case of fast ion conductors, there will be constant number of charge carriers are there, which are temperature dependent. Whereas normal ion conductors having small number of charge carriers, though they are temperature dependent. Fast ion conductors basically the conduction process takes place by means of point defects or charge carrier concentration of the order of 10 to the power 12 per centimeter cube. In the case of normal ion conductor, the conduction or the concentration, the charge carrier concentration roughly about 10 to the power 18 per centimeter cube. And how do they mobile in the lattice? There will be a low activation energy less than 1 electron volt in the case of a fast ion conductor. And if it is a normal ion conductor, as normally they are almost behaving like insulators, and they may be showing activation energy for ionic motion maybe around more than 1 electron volt, about 2 electron volt, and sometimes more than that. And if you classify these superion conductors, we can classify according to the conducting species. One you call it as cation conductor, like lithium, sodium, silver, copper, and proton. And whereas if you consider anion conductors, you have oxygen and fluorine and so forth. So cation conductors, we are very well aware the lithium ion batteries or the upcoming sodium ion batteries are here. Before lithium, there were a lot of applications of silver batteries also we have seen. And copper is not that much used, but still as academic purpose, people have studied copper ion conductors. And when coming to anion conductors, oxygen and fluorine. So oxygen conductor basically used in fuel cells, and fluorine ion conductor also used in the case of sensors. And people have also used oxygen ion conductors and proton conductors for fuel cells. So this is where the conducting species plays a role in different type of applications. And beyond that, okay, you have ionic conductors, you have superion conductors. There is something called a category called mixed ion conductors, which normally used as anode or cathode. Basically, they will exhibit high electronic conductivity. However, they also show some ionic conductivity, which will make that intercalation and deintercalation process possible. And therefore, we use them in anode and cathode materials. Look at this diagram that I have taken from a textbook. And here you can see the conductivity and as well as the species: ionic insulators, moderate ion conductors, and fast ion conductors. You can see here insulator category, and then you have electronic insulators and conductors, then you have semiconductors, and then metals. And on the rightmost corner, I have taken some of the electrolytes which exhibit ionic conductivity, and on topmost right, I have used some of the mixed ion conductors which are used as electrode. These all belong to electrodes which will behave as mixed ion conductors, and rightmost side we are showing the ionic conductors. Ionic conductor including oxygen ion conductor, silver ion conductor, and so forth. Now there is another classification based on phase, composition, and microstructure. Consider the crystalline materials. They are sometimes ideal crystals, or sometimes the crystals with point defects, or they themselves may be having structural disorders, or we can induce defects or structural disorder externally. Those classification or those materials belong to the crystalline electrolytes. On the other hand, there will be amorphous materials which are termed as glass, or semi-crystalline material, polymer electrolytes. And polymer electrolytes are recently talked more because they are very much promising for device applications. And then if you go back to the evolution of material science, composites play a basic role, and solid state ionics also not an exception. People have also developed composites which will contain crystalline materials or amorphous materials as a matrix. And inorganic fillers, or low molecular weight polymers as reinforcing materials. So, of course, people also used nanostructures for gaining better ionic conductivity as well as better interface between electrode and electrolytes. If you see the evolution of electrolyte technology over the beginning of 2000, this century to and upcoming another 20-30 years, people started with liquid organic electrolytes. We have seen several instances that batteries used with liquid organic electrolytes are volatile, they catch fire, and therefore often we have seen in news battery exploding, all these things. But later on, at this recently, people are working on 2030 in this area. We are coming up with people with electrolytes with non-flammable and with organic electrolytes and ionic liquids based electrolyte. And another 20-30 year, people are assuming that all the batteries will be having either solid polymer electrolytes or inorganic electrolytes. So this is the scenario. We started with 2000 and upcoming anticipation that at the end of 2050 or even before, there will be batteries based on completely based solid state batteries comprising solid polymer electrolytes or inorganic electrolytes, which are safe to use. Coming to each category, crystalline material, as I told, the concentration of mobile ion species will be high, and there will be, as I told in the previous slide, there will be vacancies or disorders. Based on that, the vacant ion will be moving from one side to another side, and they don't need much of the activation energy. And for example, the basic examples can be sodium beta alumina, which was commercialized and also used in high temperature sodium sulfur batteries. Silver iodide, people have also used batteries in pacemakers and so forth. Lithium nitrate, silver sulfide are the classic examples for crystalline materials. There's another classic material I just would like to say, that is silver iodide, because in previous slide I told sometime phase transition also give disorder, which will give you the better ionic conductivity. The beta AGI undergoes a phase transition at 147 degrees Celsius and become alpha AGI, and you can see the conductivity. There will be 2 order of magnitude of beta A to alpha AGI, and if it goes beyond 557, it gets in molten state. So you can see a hue, this profile is changing the ionic conductivity when the material changes from beta state to alpha stage. So this type of disorders will give you high ionic conductivity in the materials. So people have started working on how to improve. That is a typical researcher's aptitude. How to improve it further? Can we do something to have ionic conductivity better than this? So people have started working on late 90s, that stabilization of the open structure. Look at this diagram or look at these values. Beta AGI less than temperature 147 degrees Celsius. The conductivity is of the order of 10 to the power minus 6 Simon per centimeter. After it has undergone to a phase transition, see there is 5 orders of enhancement in the conductivity. It becomes 147 degrees Celsius. And there is something called stabilization, the open structure. The structure which was there enabling the ionic conductivity, which has got to be stabilized. What they did is they mixed rubidium iodide with the silver iodide. See here, this is ionic conductivity of 10 to the power minus 6. Rubidium iodide, the conductivity of the order of 10 to the power minus 12 Siemens per centimeter. It's typically a insulator, you can say. And you end up with a material called rubidium silver iodide. And if you see the conductivity, that is -3 Siemens per centimeter, which you got in silver iodide at 147 degrees. See this, the impact of research or the impact of novel idea of adding rubidium iodide and silver iodide. We call it as rubidium silver iodide or stabilized silver iodide. Similarly, silver iodide and silver phosphate, and it with silver based Ag7I4P4, and that is phosphate having with iodine, that has also got conductivity of the order of 10 to the power -2 Siemens per centimeter. So this is how the conductivities has been enhanced or realized in crystalline materials. Another classic material that people have used is sodium beta alumina. There are two structures, alpha and beta, depending on the composition of alumina. Basically, it's a sodium oxide with alumina. So you get a structure. You can look at this structure over here. You have a spinal block, and there is a small the arrangement of atoms in a vertical or section. It has reduced. Again, you have a spinal block, and again a narrow block. It's like a bottleneck structure, and these yellow colored larger spheres, which I am showing here, they are enabled to travel in this open structure. Okay, and one can make this sodium beta alumina being a ceramic in different shapes and sizes, but still people are trying to make these beta alumina in the form of a thin film, so that when you use that iron or material in a battery, the apparent resistance will be decreased. Similarly, this is another structure which we call it as well-known nasicon. Again, this can be made into the polymer, this can be made into a sheets, but still there are a lot of issues when you want to use with realistic battery applications. Still people are working on making this into a thin film and utilizing properly over a wide range of temperature, wide range of potential. All these are still challenging. And as I told before, you can stabilize the structure or you can create vacancies externally. So for example, here is a classic oxygen ion conductor, either yttrium oxide or zirconium oxide. So you add yttrium oxide in zirconium oxide, or you have calcium oxide and zirconium oxide, you can generate vacancies. Accordingly, these are called as yttrium stabilized zirconia, yttrium stabilized zirconia, or calcium stabilized zirconia, to create the vacancies, oxygen ion vacancies. And therefore these materials are again classic materials in solid state fuel cell oxygen, high temperature fuel cell applications. Challenges. When you look into this perspective of solid electrolytes, the challenges are dimensional control. We cannot make the reduction in the dimension so that we can reduce. Conductivity may be high, but unless you reduce the dimension, you cannot change the resistance. Resistance should be very minimal when you use it in a device. And mechanical properties may not suitable for device fabrication. As I told, they may be fragile and they may not give you good. And the structures are complex. The composition is complex. So one has to really have a control of synthesis of complex structures and compositions. The next category comes glass, ceramics, and polymer electrolytes. It's a intercalate, or you can say interjunction. You have ceramics, glass, and polymers based on amorphous or semi-crystalline materials. So far we have seen crystalline materials. Now we are getting into semi-crystalline or amorphous materials. Coming to amorphous materials, we can classify glassy electrolytes, as if a glass can be defined as amorphous solid without Lagrange order, or period without having Lagrange order in periodicity of arrangement of atoms. And any glass that you have, it will show a characteristic thermal parameter called as glass transition temperature. Let us look at one of the classic ionic conductor, glassy ionic conductor. A glass is composed of two things. One is glass former. They are basically oxides of silica, boron, phosphorus pentoxide, sometimes the sulfides, phosphorus sulfides, and so forth. They are glass formers. They're like polymer, like a chained structure, and glass modifiers. Typically, A stands for, in the case of ionic conductors, they belong to silver, lithium, sodium, and so forth. They're all the glass modifiers. So glass former and glass modifier. Look at this reaction. A chained link of glass formers, MOM, which is getting interacted with glass modifier, typically oxides of alkali metals in our case, and they break the link, and these ions are free to move in the structure. And if you want to have further more enhancement in conductivity, people also added dopants, where A is again belong to the alkali metal that you are looking for. For example, if you are looking for lithium-ion conductor, I'll use a glass former like B2O3, and I use lithium oxide as glass modifier, and I take dopant as lithium sulfate or lithium iodide as a dopant. So for the further enhancement in conductivity. So this is what it looks like. Glassy electrolyte exhibit high ionic conductivity compared to your crystalline materials. They have isotropic properties, absence of grain boundaries, wide range of control over properties with changing chemical composition. I'll come to that changing chemical composition slightly later. But this is what happens. A phosphate chain interacts with the sodium oxide. They are broken. And whatever the periodicity you had earlier, it is broken, and you can get the open space. See, this sodium ion is free to move everywhere, wherever there is a vacancy to travel within the glass. So that makes a better ambience or better environment for the ionic motion. So this is how you can have the control over the composition. We have glass former P2O5, which is 100%, sodium oxide here, and keep on adding the content of sodium modifier, that is sodium oxide as a modifier, into the phosphate. You cannot have, keep on changing only up to 55% of sodium oxide, 45% of phosphorus pentoxide, you can attain glass. See, this is the glass. Beyond that, you won't get any glass. It can be a mixture, it can be a crystalline material. You cannot have glass properties. Glass properties limited only at this composition between 45 to, that is 100 minus 45, that is 55 mole percent of sodium oxide, and 45% of P2O5 will give you the glass, and you have wide range of composition. See, you are playing with Na2O percentage and P2O5 composition. As the value changes, the conductivity also happen to or it is resulting in change in conductivity. That is a separate part I am not bringing in here. But when you change the content of sodium oxide and P2O5, definitely there will be change in conductivity. Look at this composition 50-50, because I'm interested in 50-50 composition, 50 mole percent of sodium oxide, 50 mole percent of phosphorus pentoxide, which will give you a composition NaPO3. People call it as sodium metaphosphate. And if you check the ionic conductivity, that is roughly about 10 to the power minus 6 Simon per centimeter at 150 degrees Celsius. So it is slightly high when compared to, of course, if you just take NaPO3, that will be insulator, roughly insulator, but when it is in a glass form, it will exhibit a conductivity of 10 to the power minus 6 Simon per centimeter at 150 degrees Celsius. Can we have dopants here? Yes, we can have dopants, and also showing some characteristic graph of XRD of these glasses. As we told, there is no long range order. You can see a big hump in the XRD, and we have keep on adding sodium sulfate as a dopant, different weight percent, up to I could add sodium glass. Now, what is the result having sodium sulfate in the glass? The result will be, I can show the next slide roughly, or here I'll give the outcome little later. These are the characteristic feature when you had different weight percent of or mole percent of sodium sulfate, the glass transition temperature has decreased. That means, as I told, glass transition temperature is a significant characteristic feature of a glass. If TG has decreased, means it has weakened. The glass matrix has become weaker. That means you have a lot of open space where the ion can hop between one location to another location. And whenever you have such glasses, people have studied by means of infrared spectroscopy and Raman spectroscopy how the bonding is changing in the case of dopants, or you just take a simple glassy electrolyte. And as I told, the conductivity, these materials being ionically conducting, you cannot use the typical DC conductivity measurements. One has to go for impedance spectroscopy. Else, if you are going for DC conductivity, what happens is the electrolyte get polarized and you won't be measuring any ionic conductivity. It is you are simply measuring a apparent the resistance or electronic conductivity. As I told, you have kept on increasing the temperature from 373 Kelvin to 403 K. So the conductivity has decreased, which will result in the real part. If you consider this real part of impedance, it is roughly 100 kilo ohms. Whereas if you go for very, very low temperature, room temperature, slightly about 150 degrees Celsius, it's about 60 kilo ohms. So this is how the conductivity changes, and it is well reflected here, and the activation energy is almost the same. That means carrier concentration has changed, and the conductivity of this phosphate glass was 1.1 into 10 to the power minus 6 Simon per centimeter. After adding 25 mole percent of sodium sulfate, you could get roughly 1 order of enhancement in the conductivity at the same temperature, that is about 150 degrees Celsius. You could get 1 order of enhancement in conductivity after addition of sodium sulfate. Now, another category of these electrolyte, that is semi-crystalline materials, that is polymer electrolytes. So polymer electrolytes, basically a solvent-free polymeric system that is obtained by interaction of polymer host with the metal salt. Let us take a polymer chain represented by Ry, and you have an alkali salt. You mix it in a proper medium with high dielectric constant like acetone, nitrile and methanol. We are not using water because water is not a suitable material for electrolytes or any application, because it has a limited electrochemical window. That's why people go for acetone, nitrile, anhydrous or methanol, and you just mix salt, get dissolved in acetone, nitrile or methanol, and then you have polymer and evaporate this acetone, nitrile or methanol. You end up with polymer electrolytes which are freestanding, which you can get of the thickness of about roughly 100 to 150 micrometer. So this is how you get control over the thickness. depends on different techniques are there to cast these polymers, so that you can have a control of polymer electrolytes roughly about 100 to 150 micrometer, or even you can have thicker electrolyte. This is advantage of this polymer electrolyte. And I'm showing one example. Same sodium phosphate added in polymer, and it has different compositions, of course. There's a particular composition, the conductivity became maximum. That is, whenever you had 6 oxygens and 1 sodium, then that conductivity was maximum here. That is, I am showing here with the blue color blue color star asterisk symbol, and that is above a softening temperature. Every polymer has its own softening temperature, beyond which it becomes glue-like, or it very free-flowing. And before it free-flowing, the matrix was rigid like this, which I am showing on the like this. After softening, the chains became very fragile, and they are giving the extra power or extra support for ion to move from one place to another place. So you have two ranges of the temperature dependent conductivity: below softening region and above softening region. So what has happened on addition of salt in the polymer? This is a polymer, this semi-crystalline. You can see a well defined spherulites, and when you added salt in it, you could see that the spherulite sizes have decreased, and you can see the amorphous content has increased. Look at the conductivity here. If you remember, the conductivity we had for a glass electrolyte is roughly about 10 to the power minus 6 or 10 to the power minus 5 at 150 degrees Celsius. But when you do this same sodium phosphate in polymer, you have reached conductivity of the order of 10 to the power minus 8 centimeter inverse at 78 degrees Celsius, just above the softening point. Around 68 degrees Celsius, the polymer starting to soften, and we measured the conductivity at around 78 degrees Celsius, which is of the order of 10 to the power minus 7 per centimeter at 78 degrees Celsius. And we move further. Okay, now as we know that we have seen solid electrolytes, the crystalline materials, then we have seen semi-crystalline and amorphous materials. Now what is the scope for developing the electrolytes? This is a complete diagram I'm showing. You have a crystal and you have glass ceramic and glass. So you can have one stage of glass ceramic between glass and crystalline material, which you can consider as a solid electrolyte. A glass ceramic also considered as a good ionic conductor. I have not included here, but if you take the same sodium phosphate and make the controlled heat treatment, slowly the glass start becoming crystalline, and at one stage you can get nanostructures of the what you call de-vitrified matrix, which is shown here, and which will also give you high ionic conductivity. Now coming to this liquid electrolyte, we all know that liquid electrolytes are good and they can exhibit high ionic conductivity. But when we are use solid electrolytes, our aim is to going nearer to the liquid electrolyte, right? So what researchers have done is add this liquid electrolyte into this polymer electrolyte, you end up with a gel polymer electrolyte. We have seen crystalline materials, we have seen glassy materials, we have seen liquid electrolytes, we have seen polymer electrolytes. So in between liquid electrolyte and polymer electrolyte, you can end up with gel polymer electrolytes, which is widely used in the prototypes, or researchers are using as a prototype electrolyte for materials. Now you go for polymer electrolyte. By changing different types of polymers, you can end up with polymer foam, or you have a polymer electrolyte and glassy electrolyte. You can get solid polymer dispersion, and you can have gel polymer electrolyte, glass ceramic. Again, you can have one more composition. So like that, you can play around to make a different type of electrolyte, and each kind of electrolyte has different advantages, disadvantages, but researchers are tending to find out some solid electrolyte. That means you can make it flexible, have a good mechanical stability, at the same time you can achieve liquid right electrolyte. So coming to the composite polymer electrolyte, I am showing some of these composite polymer electrolytes over here. Same polymer electrolyte which I have shown you earlier with the composition of 6 ether oxygens and 1 sodium phosphate, 1 sodium ion. Now I'm adding different types of fillers. Here, polymer electrolyte with PEO and sodium metaphosphate act as a matrix, and different types of fillers, inorganic fillers, as I told here in the definition, homogeneously dispersing submicron size or nano size ceramic fillers into the matrix. Again, here you can play with different weight percent, because there is always composite. Everybody is aware that after certain, only up to certain level we can have the fillers. After that, there will be a blocking effect. No more the original property of the matrix is retained. Our aim is to enhance the properties of the original matrix. So here we have chosen barium titanate of different thickness, sodium 0.7 microns and 35 nanometer. And when come to the silica, it is about 14 nanometer. And there are some clay, kind of montmorillonite clays and other ceramic clay materials or fillers. You dispose these materials into the polymer, and you can look at this optical microscopy, how it has changed. These images, first 2 images I have already shown you in the previous case of sodium metaphosphate based polymer electrolyte. Now I'm adding 35 nanometer of barium titanate and 0.7 micrometer of barium titanate, 6 weight percent of again submicron size barium titanate. Here I am showing 4 weight percent of barium titanate. You can see that the spiralage structure which was there in the already reduced in the case of polymer electrolyte, it further reduced when you added the nanometer size fillers that is of different thickness, 0.7 micrometer and 35 nanometer. If you look at this conductivity as a function of filler concentration, because our aim is to optimize any property whenever you had reinforcement material in the matrix. Filler content changes from 0 to 10 weight percent, and the conductivity enhancement. This is my host polymer electrolyte or pristine polymer electrolyte. You kept on adding weight percent of the fillers. Here I am using other fillers as well. Sodium silica, barium titanate of 2 different diameters or the particle sizes, and montmorillonite, a mixture of several oxides. Montmorillonite basically is a clay. It contains several kind of inorganic oxides. So look at this. Out of these, I am very much interested in this barium titanate, which is having 2 different particle size. The blue color one, which is having ionic conductivity at roughly around 6-8%, and whenever you had this red color diagram or symbols, that is 35 nanometer, which is top. So you had roughly when you by adding about 4-8% of fillers, you could get enhancement in ionic conductivity from -7 to -5. That means you got 2 orders of enhancement in ionic conductivity when you have used composites. That's the role of composites, or the effect of adding fillers. And again, you could see that nano fillers have enhanced the conductivity drastically. This is submicron size. Still, it is very high compared to your host matrix. And when you have used nanometer scale particles, it has reached up to minus 5.4 roughly and that is the conductivity of the polymer electrolyte. And then there is one more category, that is plasticized polymer electrolyte. Here, before coming to this, you could notice that whichever we had earlier, electrolyte, solid polymer electrolyte, which was showing conductivity of the order of -8 at 78 degrees Celsius, now it has increased by 2 orders. Now there is another way of enhancing the conductivity, that is plasticizing the polymer electrolyte. Plasticizer means something which is giving lubricant kind of effect. Unlike the ceramic fillers, they are solid, but in this case we are adding some of the polymers which are organic solvents like propylene carbonate, ethylene carbonate. If you consider polymers, low molecular weight polymers, polyethylene glycols, which is having molecular weight about 400, 600, which is of the form of liquid. These low molecular weight polymers are in the liquid form, or propylene carbonate also, which is again a liquid organic solvent. You add these materials in different weight percent into the matrix. So what happens then? Here is a better diagram by means of optical micrographs. I had to change this magnification to visualize the spherulites and enhancement in this is dark region, which shows the enhancement in the amorphous nature. So when compared to this is 20 magnification into 20 into 40. You can see the spherulites have very diminished and they got a darker area, which is confirmation of enhancement in the amorphous phase. Similarly, you added propylene carbonate, so you have a large amount of dark region which corresponds to the amorphous region, and another 10 minutes. And you had this enhancement in the amorphous phase, that is about roughly adding 50 weight percent of propylene carbonate. With this image, we could see the enhancement in enhancement in the amorphous phase. We are also proven this by means of differential scanning calorimetry, where you can calculate the amorphous percentage or crystallinity of the host polymer. So here you can see that for that reason, when you have added polymer, the degree of crystallinity that you calculate, we could calculate was 62%. When we added salt, it reduced to 37%, roughly 50% reduction. And then we kept on adding this polymer electrolyte, polyethylene glycol, a low molecular weight polymer in different weight percents. The crystallinity has decreased, which have proven the images that we have seen in the optical micrographs. Now look at this, the diagram which shows temperature dependent conductivity as a function of temperature dependent conductivity as a function of different compositions, 30, 40, 50. Unlike composites, as we increased the content of polymer, that is polyethylene glycol, the conductivity also enhanced. Look at the image that I have shown you graph before that. There was 2 different regions for conductivity in the case of host polymer, that is polyethylene oxide and sodium metaphosphate. That is the region below softening and above softening. Now that softening has not visible, but it's a smooth transition. There is smoothly, continuously that has happened, and conductivity has enhanced. As we increase the content of polyethylene glycol, the conductivity also enhanced. That means here we could not add further amount of polyethylene glycol because the original structure, what we want a freestanding polymer electrolyte. The freestanding nature of the polymer is lost because it has a more liquid content. You cannot peel off, or you cannot take it as a freestanding polymer electrolyte. Therefore, we have to limit the content of polyethylene glycol up to 78%. And you could get the enhancement in conductivity of the order of 10 to the power minus 5 at 65 degrees Celsius. So upon adding this particular slide, you can see that upon adding barium titanate, you could come the ionic conductivity of the order of minus 6 Simon per centimeter at 78 degrees Celsius, which is, if you remember the previous one, which was at around 78 degrees Celsius, that was 10 to the power minus 8. So you got enhancement in 2 orders of magnitude. And when you go for plasticized polymer electrolyte, we could get roughly 3 order of enhancement in the conductivity. Because I'm saying 3, because I'm no more measuring the ionic conductivity at 78 degrees Celsius. I'm measuring the 65 degrees Celsius, and I'm getting the conductivity of the order of minus 5 Simon per centimeter. So this makes that how you can, this is a typical classic example where you can change a conductivity of crystalline solid crystalline metaphosphate up to, that was insulator. Now it is like ionic conductivity of the order of minus 5 Simon per centimeter. A huge drastic change in ionic conductivities. So here you would have noticed 2 things. And I told in the beginning as well, how do you recognize that material is a ionic conductor? By means of it transition the transport number. The transport number will say 2A. One is ionic transport number or electronic transport number. Electronic transport number means ratio of electronic conductivity to total conductivity. It will be very, very low. Whereas to go to the ionic conductivity, the ratio ionic transference number, that is the ratio of ionic conductivity to total conductivity, and it will be tending to 1. Now you would have wondered why it is TNA, that is the transference number of sodium ion is 0.40 and 42, and what is else, isn't it? So, but here in this case, we have calculated both electronic conductivity transference number and ionic transference number. When we measured electronic transference number, it was tending to 0, that is 10 to the power minus 4. Whereas we measured, there are different techniques to measure transference number. One of them is this particular ACDC method we call, and in that case the transference number of sodium ion is 0.40, that means roughly 40%. So then what else was conducting? Ionic was 0, electronic was 0, ionic was roughly 0.4, that is 40%. What else was moving along? What is the species which is conducting? Basically, in the case of polymer electrolyte, the disadvantage is that here you don't have simply sodium ion alone. You may be having other species like Na2, Na3, which are having multiple complex, because here you have oxygen of polyethylene oxide and sodium, which is having a link. There may be different kind of ion groups will be forming, and those ion groups also mobilized in the matrix. However, still people are working for to improve, finding out a better way to determining this transport number, as well as to identify what are the other species which are conducting. As of now, the conducting species are the groups of ions which are propagating or which are moving in a matrix. This is a technique, that's what I was showing. There are Wagner's polarization, which will just polarize and check the initial current and final current, and you say that it is ionic conducting or electronic conducting. Here there is a technique called combined AC-DC technique, where you use a sodium ion conducting material. I am working on sodium ion material, so I am using here sodium ion conducting material sandwiched between 2 sodium blocks. We call this configuration as non-blocking electrode configuration, and you run impedance spectra. Okay, and thereafter you subject it to DC polarization. That means you subject to a battery, you connect to a voltage source, and you see that how the current is depleting. Initially, the current value is high because that is a combination of both electronic and ionic combination. Since it is a ionic conductor, polarization takes place over a period of time. The current will be decreasing. Earlier, it may be 5 milliamps. After waiting for about 12 to 18 hours of time, that 5 milliamps current would have reached to microamps region. That means the current has decreased, resistance is increased. From where that resistance increased? Because of polarization of the ions. So here what we do is, we also calculate I infinite, that is the polarization current, and determine what is the transport number of sodium ions. So the percentage of sodium ions which are mobilized in the matrix. So to summarize, I am giving this example which I have explained. We had a sodium phosphate salt which was showing conductivity of the order of -8 Simon centimeter at 250 degrees Celsius. When it became glass, that means you melt it and quench it, you get a glass which has shown conductivity of the order of 10 to the power -6 Simon per centimeter at 150 degrees Celsius. When you added dopant, it has further enhanced by one order. That is in the case of amorphous materials. When you look into the same sodium phosphate salt in semi-crystalline materials, you could see further enhancement in the conductivity. Rather, at lower temperature, you got similar, maybe slightly higher conductivity compared to the glass, but at much lower temperature. Here we could not measure the conductivity 150 degrees Celsius because after softening, it becomes free-flowing liquid. We cannot measure the conductivity as such at 150 degrees Celsius, and the stability of the polymer also goes bad. That's why we cannot go up to 150 degrees Celsius. So at 78 degrees Celsius, that was the conductivity. Then you made a composite electrolyte. Further, you could get 2 order of enhancement in the conductivity and see that the transport number also enhanced. And when you had a plasticized electrolyte, the conductivity is further increased. Though the temperature is lower, the conductivity looks -5 at a much lower temperature, and transport number also increased to 0.42. And with this, I will conclude my lecture explaining different kinds of electrolytes, possible electrolyte. There are crystalline, glassy, that has amorphous, semi-crystalline materials, and composites, and how one can tailor make or enhance the conductivity of a typical material. And with this, I'll conclude my lecture and wish you all happy Christmas and a bright, prosperous new year ahead in 2023.
Thank you, Professor Bhide, for this nice talk, enlightening talk. Merry Christmas to you, and Happy New Year 2023.
Thank you, sir.
Yeah, I request you to stop your screen presenting. Stop presenting.
Okay.
Yeah. Stop.
Yeah, I stopped.
Yeah. Okay, so we will take a question answer.
Yeah.
So this is from Dr. Pradeep Malji.
Huh?
How feasible are iron composite ions?
How feasible are iron composite ions? I didn't get the basically iron conductors are iron based Fe ion conducting materials are not still explored. People are working on iron based batteries, but they are like that is taking place not as a conductor. There's oxidation reduction taking place. That mechanism is going on, but iron composites, I'm not aware.
Okay, sir.
Okay.
So this next question is zinc ion also popular for energy storages?
Zinc ion.
Ions are are they popular for energy storages?
Recently, people have started not as a zinc ion conductor. They have a structure which will make you the oxygen and conductors. So zinc air batteries basically they're much more used. Basically, zinc oxide belong to the category of semiconductors or mixed ion conductors, and you can have this. They will enable oxygen ion motion.
Okay, thank you, sir.
Okay.
Many concern the disposal of batteries with
Yes.
electric vehicles development.
Yes.
So, any are there future for batteries which are recyclable?
Yes.
Are the future batteries that you shown the polymeric future batteries are they recyclable?
Yes, they are recyclable. This type of electrolytes are used in batteries, and there can be for rechargeable batteries. And since over a period of time, polymer get deteriorated or it may get damaged of because of thermal runaway of several charging and discharge process. Because we are using polymer electrolyte few micron size in between electrodes, right? So what happens is you cannot recycle it, but you can. It makes our job easy to take the electrodes, either of the electrodes, anode, cathode. Recycling anode, cathode become easier than the electrolyte. Electrolyte normally of no use. You cannot recycle it. It's become a waste. Maybe organic chemists can resynthesize that if it is could get it. Normally over a period of cycle, these polymer loses its strength, and this polymer, since it has loss and strength, separation of anode cathode will be easy and you can process them better. If you make everything solid electrolyte, you have a block of solid electrolyte in between two electrode, then again separation, everything will be difficult.
Okay, okay. So this next question is on the same lines.
Yeah.
Will the polymeric electrolytes degrade if not used for a long time?
No. No.
Okay. So generally, I think
Not means in the sense you are using a battery, you are
batteries.
already assembled in a battery. If you
Yeah.
don't use the battery for long, nothing happens. As such, your liquid batteries.
Okay, okay. So they
They
have
just
the
maintain. Yes.
properties. Okay,
Yes.
the properties are intact. And
Yes.
also maybe another parallel question. So you had shown something like temperature dependency for the polymeric electrolytes and
Yes. Yes.
78 and then 68 degrees centigrade.
Yes. Yes.
So for the colder environments, like suppose our Himachal and all that, border
Yes.
lines.
Yes.
So there, these kinds of electrolyte or batteries or energy storage polymeric electrolytes are they stable or?
Yes. Yes. See, normally nowadays people are using ionic liquids in the polymer matrix. So that
Okay.
makes because ionic liquids are molten stage at room temperature itself. So even if you go to the frozen case, some of these ionic liquids will be still in the fluidic stage. So it will give you a better conductivity even if you go for lower temperature. So it's basically additives. Here I have used up to room temperature because the conductivity is very low. But when you use some other additives like ionic liquids or some other polymers, which will get frozen at much more than room temperature, then still you can get in much more conductivity. That's the thing. Here I limited to the crystalline, so above room temperature. But when you have additives like liquid, definitely you can have the conductivity much more lower. At present, people are using organic solvents, which will get what you call molten above minus 60 degree or something like that.
Okay, thank you. So, Professor Bide, this is last question. The ceramic fillers that
Yes.
you had shown,
Yes. Yes.
do they keep homogeneity in the polymeric
Yes.
electrolytes after few cycles of operation?
Yes, you can. You can. Basically, what they do is normally polymer electrolyte is amorphous. It's a metastable state, right? It will tend to crystalline. isn't it? To avoid that crystallinity becoming crystalline, you have these fillers act as a centers which will delay the crystallization process. So it will still retain the amorphous phase. And there are fillers, there are variety of fillers. Sometimes you use surface group enhanced fillers, which will make the ion to come near and provide a easier pathways to travel.
Okay.
But they will still give a better performance than the pristine polymer electrolyte.
Okay.
And they become very neutral for electrodes, and they don't get decomposed because of any potential that you apply and so forth.
Okay, thank you. I think there are no further questions.
Yeah.
So we thank you for your time and for this Treats Talk 17.
Thank
It's
you.
a pleasure to host you
Yes, sir.
online. Plus,
Yes.
But please visit IIT Dharwad
Yes.
whenever you get a time, and then
Definitely.
have in-person interactions as well.
Definitely, because Karnataka is my hometown, right?
Yes, yes.
Definitely, I make a visit, and nice meeting you, Dheeraj, Dr. Dheeraj, and I think your colleague was Pradeep. Huh? Yes.
Praveen, Dr.
Yeah.
Pradeep is also there. Dr.
Yeah.
Pradeep has
Yeah.
a PhD from IIT Madras. I don't know whether you have met
Okay.
him, from Applied Mechanics Department.
Okay, fine. Nice meeting you all, sir, and thank you for the opportunity, and wish you again happy year end and a new beginning with a lot of, though there are some uncertainties that started, but we'll hope for the doing best.
Yes, definitely.
Yeah.
Yes. Thank you.
Thank you very much.
Thank you.
Bye.
Thank you.